In this video, we'll be exploring something called trigonometry, which comes from Greek words meaning to measure triangles. Among other uses, trigonometry was used to solve problems involving measurement, especially when it is not easy to measure something directly. For example, we'll explore how to place a ladder in a safe position. As was said, we use trigonometry to measure triangles, and in grade 10 we measure right triangles specifically. In a triangle, we can measure its angles and its side lengths. To begin our exploration of trigonometry, take a look at these three triangles. What do you notice? What are some relationships you can see? To see some relationships, it may help to arrange the triangles like this. We can see that their corresponding angles are equal. And you may have noticed some relationships among the side lengths as well. For example, the green triangle sides are double that of the orange triangle, and the blue triangle has sides that are 3 times that of the orange triangle. The sides that are similarly situated within each triangle are called corresponding sides, and we can see equivalent ratios between these pairs of sides. What other equivalent ratios can you find? One set of equivalent ratios we can find just by inverting each fraction. There are many other possible ratios. Here are a couple of them. Let's take a look at 3 of these ratios with the large triangle. These ratios are defined in trigonometry with respect to the 37-degree angle. The first is the tangent ratio, which is abbreviated by tan. The second is called the sine ratio, which is abbreviated by sin. The third is called the cosine ratio, which is abbreviated by cos. These 3 ratios can also be expressed as decimals, and these decimal values apply no matter the size of the similar triangle. If we invert these ratios, we get the tangent, sine, and cosine of the 53-degree angle. Let's generalize these ratios for any triangle. We begin with an angle, and a common variable that is used for an angle is the Greek letter theta. An angle measures the rotation between 2 rays. The side of the triangle that these rays extend to is called the opposite side. The shorter side right next to the angle is called the adjacent side. The longest side is called the hypotenuse. We can now define the 3 trigonometric ratios using these labels. The sine ratio is opposite over hypotenuse. The cosine ratio is adjacent over hypotenuse, and the tangent ratio is opposite over adjacent. Take a look at the first letter of each of these words. If we focus on them, we can form a phrase that can help us to remember how these ratios are defined. We pronounce this as SOHCAHTOA. When solving problems involving trigonometry, we involve the angle, 2 sides, and the ratio. So the problems we need to solve involve determining one of these, that is, a ratio, a side length, or an angle. Let's apply what we have learned to solve some problems. In this first example, we are asked to find 3 trigonometric ratios. We can use SOHCAHTOA to help. How do you think using SOHCAHTOA can help us solve this problem? To determine sine A, we need to express the ratio between the opposite side and the hypotenuse. Relative to angle A, the opposite side is BC. The hypotenuse is AC, so the sine of A is 5/13. For cosine A, we need the adjacent over the hypotenuse. Relative to angle A, the adjacent side is AB, and once again, the hypotenuse is AC. So the cosine of A is 12/13. Finally, for the tangent of angle C, we need the opposite over the adjacent. Relative to angle C, the opposite side is AB, and the adjacent side is BC, so the tan of angle C is 12/5. There are other ratios we could determine. For example, what is the cosine of angle C? And once you've found it, what do you notice about it? Cosine C is adjacent over hypotenuse, which we can see is 5/13. What you may have noticed is that it is the same as the sine of angle A. This will always be true of the acute angles in a right triangle, that the sine of one of the angles is the same as the cosine of the other angle. In our next problem, we are given some information and then asked to determine the lengths of an unknown side in each triangle. Which trigonometric ratios can you use to figure out these side lengths? We can use SOHCAHTOA to figure out which ratios to use to calculate the missing side lengths. In the first triangle, we are given the hypotenuse and asked to find the side opposite the given angle. So we can use the sine of 29.3 degrees and express that as the ratio of x to 14. In the second triangle, we are given the adjacent side and asked to find the hypotenuse. So we can use the cosine of 72.2 degrees and express that as a ratio of 5 to y. We now have equations that we can use to solve for the unknown side lengths. To solve each one, we need to isolate the variable, which means to get it on its own. In the first equation, we can isolate x by multiplying both sides of the equation by 14. We can use a scientific calculator to multiply 14 by the sine of 29.3 degrees. The answer is approximately 6.85. In the second equation, we first need to multiply both sides by y and then divide both sides by the cosine of 72.2 degrees. Now that y is isolated, we can use a scientific calculator to divide 5 by the cosine of 72.2 degrees. Our answer is approximately 16.36. Let's take another look at how we solve the second equation. If we compare these two statements, notice that the cosine of 72.2 degrees and y have switched places. This equation solving technique is helpful whenever our equation involves dividing by the variable. What if we wanted to solve for the length of the third side? How could you figure that out? One approach we can take is to use trigonometry. Z is the opposite side, and 5 is the adjacent, so we can use tangent, and this ratio is z over 5. To solve the equation, multiply both sides by 5. Next, we use a calculator to determine 5 times the tangent of 72.2 degrees, so z is approximately 15.57. But we actually didn't have to use trigonometry, as we could have used the Pythagorean theorem instead. By this theorem, z squared plus 5 squared equals 16.36 squared. To isolate z, we first need to subtract 5 squared from both sides. Then, to undo the square, we need to take the square root of both sides. This gives us that z is approximately 15.58. Note that our answer is slightly different this time. This is because we used an approximate or rounded value in our calculation, so our answer is less accurate. Generally, it's recommended that we avoid using approximate numbers when we can, or to extend them to more decimal places. Our next problem involves determining missing angles in a right triangle. How can trigonometry help us figure out these angles? Using SOHCAHTOA with angle A, the two given sides are the adjacent side and the hypotenuse. So we need to use cosine, and this ratio is 17/18. For angle C, we still have the hypotenuse, but the other side is opposite. So we need to use sine, and the ratio is also 17/18. To solve for angle A, we use what is called the inverse function, which looks like this. The -1 in this case does not represent an exponent, but simply the inverse relation. When using a scientific calculator, one usually needs to use an inverse key or second function key. Calculating the inverse cosine of 17/18 gives us that the angle is approximately 19.2 degrees. To solve for angle C, we calculate the inverse sine of the ratio, which is approximately 70.8 degrees. Notice that if we add these two angles, we get 90 degrees. This is because the sum of angles in a triangle is 180 degrees, and one of the angles is 90 degrees. So we could have calculated angle C by subtracting angle A from 90 degrees. Our next problem refers back to something mentioned at the beginning of the video, which involves figuring out how to position a ladder to be at a safe angle. It is inconvenient to measure an angle for the ladder, so instead we can use the distance from the base of the ladder to the wall. Trigonometry helps us to use what's called indirect measurement. In this case, we can place the ladder at a specific angle by measuring a length instead of an angle. As we change the distance of the base of the ladder from the wall, the angle changes. Health and safety guidelines recommend that a ladder be placed at a 75-degree angle. If this ladder is 10 feet long, how far away from the wall should this bottom part of the ladder be placed? We can model this problem using a right triangle. For the 75-degree angle, the two sides we are working with are the adjacent and the hypotenuse, so we need to use the cosine of 75 degrees. And this ratio is d/10. Multiplying both sides by 10 gives us that d equals 10 times the cosine of 75 degrees, which we calculate to be approximately 2.59 feet from the wall. Practically speaking, we should convert this into feet and inches. 0.59 feet is approximately 7 inches, so the distance is better expressed as 2 feet 7 inches. Our final problem is also an example that uses indirect measurement. It is to figure out the height of a tree, which cannot be done directly. To solve this kind of problem in real life, one can use a special device called a clinometer, which one can use to measure an angle from their eye to a distant point. As one tilts the protractor, the bob stays vertical and can thus read us an angle. Suppose a person standing on a nearby hill uses a clinometer. They measure what is called the angle of elevation to be 16 degrees. They then measure what is called the angle of depression to be 13 degrees. The angles of elevation and depression are measured relative to a horizontal line. The distance from the person to the base of the tree is 21 meters. So, with this information provided, how could you approach solving this problem? Even though the large triangle is not a right triangle, we can break it up into two right triangles. We'll use the variable a to represent this portion of the height of the tree. Using trigonometry, we can identify a tangent ratio and see that a is equal to 21 times a tangent of 16 degrees, and that's approximately 6.02 meters. In a similar fashion, we can set up the other right triangle and use a variable like b to represent the height of the other part of the tree. Again, using trigonometry, we can see that b is 21 times the tangent of 13 degrees, and that's approximately 4.84 meters. Adding these two heights together gives us the height of the whole tree to be approximately 10.84 meters. This video addresses several learning standards in the Foundations of Mathematics and Pre-Calculus 10 curriculum. Proportional reasoning emerged through the trigonometric ratios in similar triangles. We also highlighted how trigonometry is a powerful concept for modeling and solving problems to measure things indirectly. In this content standard, we focused on the primary trigonometric ratios of sine, cosine, and tangent. As your child learns about trigonometry in their classroom, several curricular competencies may emerge. For example, we both explored and applied trigonometry to make sense of problems involving right triangles and how to use a calculator to determine the answers to problems. We used trigonometry to model and solve the problems involving where to place a ladder safely, as well as determine the height of a tree. And finally, a lot of new language was learned in this concept, including the names of the ratios and the names of the sides. We hope that you found this video valuable in helping you support your child in their learning about trigonometry. Be sure to check out the other titles in this series.